Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase induction motors. By solving this problem, we shall learn how to determine overall efficiency and shaft torque of a three-phase induction motor for a particular value of slip when parameters of its exact equivalent circuit are given. A 50 HP 420 volts 50 Hz 10-pole 3-phase mesh connected induction motor has following per phase parameters referred to stator side. R1 equals to 0.19 ohm, X1 equals to 1.12 ohm, R2 dash equals to 0.29 ohm, X2S dash equals to 1.12 ohm, Rc equals to 143 ohm and Xm equals to 16.8 ohm. The rotational losses amount to 345 watts. The slip is 2.6%. Using exact equivalent circuit, we have to calculate rotor speed, stator current, stator power factor, air gap power, mechanical power developed, power output, developed torque, shaft torque, and efficiency. Let us first write down the given data. For rotor winding, resistance per phase referred to the stator R2 dash equals to 0.29 ohm and standstill leakage reactance per phase X2S dash equals to 1.12 ohm. For any value of slip S, rotor impedance per phase referred to the stator Z2 dash equals to R2 dash by S plus JX2S dash. Given slip S equals to 2.6%, that is equal to 0.026 per unit. Therefore, Z2 dash equals to 0.29 by 0.026 plus J times 1.12 ohm, that is equal to 11.1538 plus J times 1.12 ohm. This may be written in polar form as 11.21 ohm at an angle 5.734 degree. For shunt branch, given resistance per phase representing coal losses Rc equals to 143 ohm and magnetizing reactance per phase Xm equals to 16.8 ohm. Let us now calculate Rc plus Jxm, that is equal to 143 plus J times 16.8 ohm. This may be written in polar form as 143.9835 ohm at an angle 6.7 degree. Expression for no load shunt impedance per phase Z0 equals to Rc parallel with Jxm, that is equal to Rc into Jxm divided by Rc plus Jxm. Using values we get 143 into 16.8 at an angle 90 degree divided by 143.9835 at an angle 6.7 degree, that is equal to 16.6852 ohm at an angle 83.3 degree. This may be written in Cartesian form as 1.9467 plus J times 16.57 ohm. Now we shall calculate Z0 plus Z2 dash. Using values we get 13.1005 plus J times 17.69 ohm. This may be written in polar form as 22 ohm at an angle 53.48 degree. Now we shall calculate equivalent impedance per phase. ZEQ equals to Z0 parallel with Z2 dash that is equal to Z0 into Z2 dash divided by Z0 plus Z2 dash. Using values we get 16.6852 at an angle 83.3 degree into 11.21 at an angle 5.734 degree divided by 22 at an angle 53.48 degree. That gives us 8.5 ohm at an angle 35.554 degree. Given line-to-line terminal voltage VL equals to 420 volts. For mesh-connected induction motor, terminal voltage per phase ET equals to VL equals to 420 volts. For stator winding, given resistance per phase R1 equals to 0.19 ohm and leakage reactance per phase X1 equals to 1.12 ohm. Expression for stator impedance per phase Z1 equals to R1 plus JX1 equals to 0.19 plus J times 1.12 ohm. We have computed equivalent impedance per phase ZEQ equals to 8.5 ohm at an angle 35.554 degree. This may be written in Cartesian form as 6.9153 plus J times 4.9425 ohm. Let us now calculate total input impedance per phase Zin equals to Z1 plus ZEQ. Using values we get 7.1053 plus J times 6.0625 ohm. This may be written in polar form as 9.34 ohm at an angle 40.472 degree. Expression for stator current per phase I1 equals to ET divided by Zin. Taking terminal voltage per phase ET as reference, we get I1 equals to 420 at an angle 0 degree divided by 9.34 at an angle 40.472 degree. That gives us 44.9679 ampere at an angle minus 40.472 degree. In polar form, we can write stator current per phase I1 equals to I1 at an angle minus phi1 equals to 44.9679 ampere at an angle minus 40.472 degree. Expression for rotor current per phase referred to stator side I2 dash equals to Z0 divided by Z0 plus Z2 dash into I1. We have determined shunt impedance per phase Z0 equals to 16.6852 ohm at an angle 83.3 degree and Z0 plus Z2 dash equals to 22 ohm at an angle 53.48 degree. Using values we get I2 dash equals to 16.6852 at an angle 83.3 degree divided by 22 at an angle 53.48 degree into 44.9679 at an angle minus 40.472 degree. That gives us 34.1 ampere at an angle minus 10.652 degree. For three-phase induction motor, expression for air gap power PG equals to 3 times I2 dash square into R2 dash by S. Given per phase rotor resistance referred to the stator R2 dash equals to 0.29 ohm and slip S equals to 0.026 per unit. Therefore, Pg equals to 3 into 34.1 square into 0.29 by 0.026, which is approximately equal to 38,909.4 watt. Mechanical power developed, Pm equals to 1 minus S times Pg. Using values we get 1 minus 0.026 into 38,909.4, which is approximately equal to 37,898 watts. For mesh-connected induction motor, stator line current IL equals to √3 times I1, that is equal to √3 into 44.9679, that is equal to 77.8867 ampere. Now we shall determine stator power factor. Cos phi 1 equals to cos of 40.472 degree, that is equal to 0.76 lagging. For three-phase induction motor, total input power Pin equals to 3 times Et into I1 cos phi 1. Using values we get 3 into 420 into 44.9679 into 0.76, which is approximately equal to 43,061 watts. Now we shall calculate total power output. PO equals to PM minus PR. Given rotational losses, PR equals to 345 watts. We have computed mechanical power developed. PM equals to 37,898 watts. Therefore, PO equals to 37,898 minus 345, that is equal to 37,553 watts. Now we shall determine overall efficiency of the motor. Eta equals to PO divided by Pin. Using values we get 37,553 divided by 43,061, that is equal to 0.872 per unit or 87.2%. Given number of poles of the machine P equals to 10 and supply frequency F equals to 50 Hz. Let us now calculate synchronous speed. Ns equals to 120 F by P. Using values we get 120 into 50 divided by 10, that gives us 600 revolutions per minute. Expression for rotor speed Nr equals to 1 minus S times Ns. Given slip S equals to 0.026 per unit. Therefore, Nr equals to 1 minus 0.026 into 600, that is equal to 584.4 revolutions per minute. Expression for developed torque Td equals to Pg divided by 2 pi into Ns by 6T. We have computed air gap power Pg equals to 38,909.4 watt. Therefore, Td equals to 38,909.4 divided by 2 pi into 600 by 6T, which is approximately equal to 619 Newton meter. Expression for shaft torque TSH equals to PO divided by 2 pi into Nr by 6T. We have obtained output power PO equals to 37,553 watts. Therefore, TSH equals to 37,553 divided by 2 pi into 584.4 by 6t, which is approximately equal to 613.63 Newton meter. Now we shall learn how to determine equivalent rotor current per phase I2' using Thevenin's theorem. For this purpose, we shall remove the load, that is the equivalent rotor impedance per phase Z2' from this circuit. Now the open circuit voltage as seen from terminals A and B gives us Thevenin's voltage. We have obtained stator impedance per phase Z1 equals to 0.19 plus J times 1.12 ohm. This may be written in polar form as 1.136 ohm at an angle 80.3718 degree. Rotor impedance per phase referred to the stator Z2' equals to 11.1538 plus J times 1.12 ohm, that is equal to 11.21 ohm at an angle 5.734 degree, and shunt impedance per phase Z0 equals to 1.9467 plus J times 16.57 ohm, that is equal to 16.6852 ohm at an angle 83.3 degree. Let us now calculate Z0 plus Z1. Using values we get 2.1367 plus J times 17.69 ohm. This may be written in polar form as 17.8186 ohm at an angle 83.11285 degree. Now we shall determine Thevenin's voltage. V Thevenin equals to Z0 into I, that is equal to Z0 into ET divided by Z0 plus Z1. Using values we get 16.6852 at an angle 83.3 degree into 420 at an angle 0 degree divided by 17.8186 at an angle 83.11285 degree. That gives us 393.2848 volt at an angle 0.18715 degree. To determine Thevenin's impedance, let us short circuit the voltage source. Now the impedance as seen from terminals A and B gives us Thevenin's impedance. Z Thevenin equals to Z0 parallel with Z1, that is equal to Z0 into Z1 divided by Z0 plus Z1. Using values we get 16.6852 at an angle 83.3 degree into 1.136 at an angle 80.3718 degree divided by 17.8186 at an angle 83.11285 degree. That gives us 1.06374 ohm at an angle 80.55895 degree. This may be written in Cartesian form as 0.1745 plus J times 1.0493 ohm. Now we shall calculate Z Thevenin plus Z2' using values we get 11.3283 plus J times 2.1693 ohm. This may be written in polar form as 11.5341 ohm at an angle 10.84 degree. We have determined Thevenin's voltage. V Thevenin equals to 393.2848 volt at an angle 0.18715 degree, and Thevenin's impedance Z Thevenin equals to 1.0637 ohm at an angle 80.55895 degree. Let us draw the Thevenin's equivalent circuit as seen from terminals A and B. Now we shall connect the load, that is the equivalent rotor impedance per phase Z2' back to this circuit. Let us now determine the load current, that is the rotor current per phase referred to stator side. I2' equals to IL equals to V Thevenin divided by Z Thevenin plus ZL, or V Thevenin divided by Z Thevenin plus Z2'. We have computed Z Thevenin plus Z2' equals to 11.5341 ohm at an angle 10.84 degree. Therefore, I2' equals to 393.2848 at an angle 0.18715 degree divided by 11.5341 at an angle 10.84 degree. That gives us 34.1 ampere at an angle minus 10.65285 degree. Expression for induced EMF per phase E1 equals to Z2' into I2'. We have obtained rotor impedance per phase referred to the stator Z2' equals to 11.21 ohm at an angle 5.734 degree. Using values we get E1 equals to 11.21 at an angle 5.734 degree into 34.1 at an angle minus 10.65285 degree. That gives us 382.261 volt at an angle minus 4.91885 degree. We have obtained induced EMF per phase E1 equals to 382.261 volt at an angle minus 4.91885 degree. This may be written in Cartesian form as 380.85319 minus J times 32.77686 volt. Expression for stator current per phase I1 equals to ET minus U1 divided by Z1. We have determined stator impedance per phase Z1 equals to 1.136 ohm at an angle 80.3718 degree. Using values we get I1 equals to 420 minus of 380.85319 minus J times 32.77686 divided by 1.136 at an angle 80.3718 degree. That is equal to 51.0568 at an angle 39.9388 degree divided by 1.136 at an angle 80.3718 degree. That gives us 44.9444 ampere at an angle minus 40.433 degree. So today we have solved one numerical problem on three-phase induction motors. By solving this problem, we have learned how to determine overall efficiency and shaft torque of a three-phase induction motor at a particular value of slip when parameters of its exact equivalent circuit are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.